destinations. So what happens in the case when you have the containers as a visualization technology in this scenario? What is the difference when I need to transfer all containers in a single destination versus the case when I need to segment the containers to multiple destinations? Can be due to the fact that there may be not enough computing resources to a single instance. And again, of course, as expected, as the number of containers increase, there is the interesting part is on the other figure, again in these slides, which shows basically the migration cost. So for all of the experiments, you'll see from the migration cost perspective, the large portion is related to transfer the container right from one edge instance to the second one, and then you can have the backup. That means the snapshot that I just mentioned, plus the restoration of the service to a target. I suggest at some point, at this point, maybe I can, let's say, stop my presentation. The reason for that is for this set of, let's say, slides that I just presented, where there are any, let's say, questions from the audience. I mean, you can you can. Yes. What I'm suggesting now is
Hello, sir.
yes. Hello. Yes.
Hello, sir. Actually, the it is the it is the not the end of the session. It is the intermediate time. So, as per the audience query, till now we have not received any query. But, sir, I have a query from the side of audience. Is that now we are using the industry 5.0? Am I correct, sir?
No, the trend at the moment mainly it is about we use in the industry 4.0. We are moving towards industry 5.0. So the whole idea and the difference basically is we want to facilitate machine learning and, if you like, deep learning, this kind of environment, in order to facilitate the autonomy of the systems to make the decisions, because it's a dynamic environment. So in industry 5.0 mainly refers to the fact that you may have machine learning, and also in this kind of environment, a new terminology that has been introduced is called MLOps. MLOps mainly refers to the fact that we can transform what is called DevOps today. So DevOps refers to the use of and deploy any kind of big data project in any enterprise environment. So how to, in this DevOps cycle, to adopt machine learning models. Yes.
Okay, sir. Sir, another query is that as machine learning and AI works with a large amount of data, and here
Well,
we need the yes, sir.
yeah, that's a very good question. Actually, this is part of the slides when I have a specific section which is called the road ahead. So I have already presented there, first of all, a couple of challenges associated with handling large amount of data. And this is something that I'm going to cover it at a later stage in my presentation.
Okay, sir. If from the participant, anybody want to work with this interesting region, what you are elaborating, sir, I think there will be for the experiment purpose there will be a scarcity of data. So can you say the resource of data that is where we can get such that we can continue our research program on this area?
Okay. All right. Yeah. Okay. From the research point of view, even I have something also on the road ahead as well. I have mentioned because there are a lot of the technology evolves very fast. I have already mentioned mainly to you that we have one aspect is the virtualization technology. We have already shifted from virtual machines towards what is called to containers, right? One of the problems of containers is that although they are flexible, lightweight, they lack of security, robustness, and especially in an environment which is basically um, uh, multi-tenant. That means I can host many users. So one of the problems is how to cope with that challenge. So there are two approaches on that. One is what is called unikernels. Although unikernels they are very robust and lightweight, they lack a standardized process of how you can deploy unikernels. And another technology in our days that has received attention from the research community is called WebAssembly. So WebAssembly is something new. So from the research point of view, somebody can investigate the footprint. Another aspect that somebody needs to consider in this kind of environment is the fact of we are, especially towards 6G, we have been interested for things like sustainability. So how you be able, let's say, to take into considerations the, the energy consumption, all right, the energy footprint, and to make the decisions from the deployment point of view, take into account the energy consumption as well. So this is something that somebody needs to yeah. In any case, what I'm planning at the end of my presentation, I'm going to share with you my slides. You can share them with the participants. So if there are any more questions, I'm happy to answer on that.
Okay, sir. Thank you,
Yeah,
sir. Extremely
sure,
good
sure.
insight.
Yeah. If there are any more questions, I can continue, right?
Okay, sir. Sir, another question I am having another question is that what kind of simulator you are using here?
No. Okay. That's a very good question. First of all, we haven't used a simulator. We have built a testbed environment. So this testbed environment is mainly actually we have considered a combinations of devices like Raspberry Pis, all right,
Mm,
along with
mm.
NVIDIA JSON, and we have
Oh,
used some tools. So they're already from the monitoring perspective. There is an open source tool which is called Prometheus. It's an open source tool that you can monitoring the resources that I just explained. This is one approach. In one other approach, we have used GNS3. In GNS3, basically, you can emulate your environment because it's a containerized environment and you can import devices as images. So you can build something which is quite close to reality. And in some of the scenarios that I'm going to present later on, we have used also some customized simulation tools. So the answer to that is depending of what you want to achieve. Some of the work we have done at the experimental level, so we have test beds, all right, that we test and evaluate these technologies, but we have also used simulations as well. So it's a combination.
sir, understood, sir. Very interesting area and a very interesting research direction.
Okay,
What you are
okay,
continuing, sir. Okay, sir.
okay.
Thank you, sir. You may
All right,
continue.
all right, yeah. So yeah, let me yeah. So one other, let's say, important, let's say, so we have seen more or less topics in the basically um, resource optimization and resource optimization from the computing perspective. Because you mentioned about what kind of also use cases we have investigated. One of the challenges that we have looked through our research is what we call video analytics on the edge. So what is that? So imagine that I may have some video feeds from cameras. So how to be able to optimize and generate the video analytics in this kind of environment. So the whole idea is traditionally, or if like the solutions that we have currently without the use of edge is you have some video cameras, even we have a lot of cameras in London. So the whole idea is to aggregate all these video feeds in a central point. This can be AWS or Google Cloud or any kind of hyperscaler, and then there to run your machine learning models. This kind of environment, besides the private issues, also if you don't have high-speed broadband connections, cannot give you results fast, all right? Because you have all this bottleneck of transferring all this information to a central point and then analyze that. And of course, on the top, in certain cases, you may have a problem of privacy. So the whole idea is how to be able, first of all, to provide and to analyze the services, video information. We call them video analytics, and at the same time, how from the same video feed, how to have multiple services. And I'll give you an example. Imagine that you may be in a shopping mall, all right? So I have a single video feed, right? But the interesting part is I can generate different types of information, right? That means surveillance. People will be interested for some incidents, right? But if I have retailers, the retailers are looking for different types of information. Excuse me. For example, I may be interested to see how many people have entered to a shop. So also to find if there are ladies or men that are interesting for particular products, so I can do some promotion. And this kind of information can be extracted from the same video feed. So the whole idea here is I have a single video source, but using different machine learning models, I can extract different information that can be targeted from different user groups. So the whole idea is how to make this kind of deployment low cost, all right, and scalable. All right, what we have done in this kind of research. So there are a couple of research questions. The first question is how to optimally distribute the real-time application across edge servers. So imagine that I don't have a single edge server, I can have multiple edge servers, all right? So to optimize the computing resources and to fully utilize them in an optimum manner, how to deploy these applications, and of course, how to take into consideration the fact that we deal with a very dynamic workloads. The whole idea here is, and also what I need to highlight here is, potentially we want to have a solution that is low cost as well. Because somebody may say, all right, what I can do is I can go and buy very expensive, for example, you can get some edge devices. There are already solutions from companies like NVIDIA or Intel. Of course, this can be, it's possible, but it's going to be very expensive. So what else we can do? In this kind of research, we can have something that is called virtual function chain. So what is that? I need to go back to the example, to the figure to explain that. So if I have, let's say, a Raspberry Pi, I could go and deploy the entire service to a single device and run the service. But what I can do is I can do a more clever approach when I can use a low-cost device, for example, Raspberry Pis. And as you can see, what I can do is I can instead of following a monolithic type of approach, I can segment my application to different processes. For example, in this example, you see, I may have, let's say, an initial process dealing with image enhancement, right? So I can do a video pre-processing. Another aspect of what I can do is I can do feature extraction, and then I can do in another machine, for example, I can run a CNN model. So what I can do instead of building a single monolithic application, I can uh, I can segment, let's say, my application to different processes. This kind of let's say approach is inspired from what is called virtual function chain. It's something that has been introduced by software-defined networks. The software-defined network is about the softwareization of the network infrastructure. So today's internet is based on the fact that we have routers. The routers, they have their own decisions with respect to the next hop until to reach the destination. So what is happening is to find the destination, I need to run something which is called a routing algorithm, right? And what happens is when this is completed, the routers themselves, they need to exchange this kind of information. So we have a kind of distributed approach to the internet. Software-defined network is a new approach when the devices themselves, they don't make any decisions through an API which is called northbound API. We can collect information from the different devices to a central server, and the central server then can make a decisions, and these decisions through another API, southbound API, can send the decisions about the next hop, etc. So this is the principle of SDN. So the virtual function chain is something that has come from this technology, and a fundamental aspect of that is what is called virtual network function. So you can have in practice VNF. There's nothing else but using existing computing infrastructure and run a network function. A network function can be a router, it can be a firewall, any kind of network device. All right. So in this kind of approach, what we have considered is the concept of VNF have been extended to virtual function. So a virtual function is all these blocks that I have presented in this figure. It can be an image, for example, do an image enhancement, or this is a virtual, another one virtual function. Another one can be the feature extraction. Another one may be to do the CNN classification, and then I can have the inference model. So all this can be different uh, virtual functions. At the end of the day, in this kind of distributed kind of approach, the whole idea is I need something that I need to link all of them together to provide at the end of the day a service. Don't forget it's about the service. And what we need for that is something which is called virtual function orchestration. So, so a set of virtual functions specific for a specific service. So as I mentioned, you may have a service related to the surveillance. Another one related, let's say, to maybe to have a personalized advertisement. So you need for all of those to deploy the virtual functions as explained, and at the end of the day, you need to link them all together. So this is an example, all right? So imagine that you can have with green colors the virtual function chain, and then at the end of the day, I can have a different path that corresponds to a different use case. It can be surveillance, it can be a personalized advertisement, or it can be, I don't know, analytics related to traffic, any kind of service. So you'll see at the end of the day, first of all, I decompose the problem because I can host all these virtual functions to not necessarily demanding edge devices. Can be even a kind of a Raspberry Pi, and then and at the end of the day, the interesting part, depending on your deployment, what kind of services, you need to have a scale, not at the monolithic service itself, but on the specific function. So you'll see in this example, I need to scale up not all functions, but a set of them that are common to the three different services, which is the use case scenario in this figure. So some of the principles that we have already considered, and then I have here a couple of um, to our this work has been presented in some in a conference and in a journal. So the whole idea here is that each service is decomposed to a set of process. So each process can implement a certain task, as I already explained. So then we have to instantiate a virtual function, and to be this function needs to be deployed at the next node. From the implementation point of view, we can have three parallel threads. One is the input queue, the other one is the output queue, and of course the running agent that implements, for example, the logic part of the virtual function. So to be able to run a service, we need an orchestrator that manages the virtual functions allocation to the physical devices and establish the communication channels among them. So, and of course, what is important is the role of the orchestrator, this orchestration, which is basically orchestration about the service deployment. So the role of that is to monitoring the performance of the service. For example, in this kind of scenario, because it's a real-time service, the constraint in this case can be how many process frames per second, or it's going to be the total cost. These are the performance criteria that somebody needs to consider for the deployment. Some other considerations. We need to consider the fact that this is a real-time service. So the QoS aspect is quite important because, as I said, it's a real-time. So again, we need to take into consideration the potential outages and failures and react appropriately. This is quite important. The proposed, as I said, framework lies with what is called virtual function orchestration. And also what is the advantage of this approach is that each VF may appear in the VFC at several instances and interconnected virtual function chain. So in practice, each virtual function chain corresponds to a different application, or if like video analytics service. So there are three types of problems here that we can consider for this deployment. First of all, one is the placement problem of the virtual functions. The second is the caching of the information, and third is the migration if there are issues with that. So first of all, we need to consider the placement problem. The placement problem is first of all to see how many instances and replicas is needed, and then the problem is to assign the instance to an edge device so that analytics are generated in order to take into consideration the cost that has to be minimized, and of course taking into account the QoS. So it's about the placement problem can be, let's say, segmented into different sub-problems. The first one is related to the instances, how many replicas are needed, and of course the placement as well. So the first one is, I don't know, it's outside the scope of the presentation to explain the massive. Somebody interested can go to the paper, have a look at that. So the first problem is to identify the minimum number of instances for each virtual function. And the second problem is to minimize the total cost, all right? Take into account the constraint, all right? Don't forget the constraint is the budget, the time budget, and the time budget is determined by the service and what is the frame per second I need to achieve, all right? This is the frame per second from the service perspective and not necessarily from what I get as an input. But of course, there must be a kind of minimum value regarding this frame per second service that needs to be displayed. So in practice, if I have a surveillance service, or if I have, let's say, a service related to, I don't know, face detection and face recognition, I would like, let's say, every few seconds, if there are people entering to the scene to appear that on the dashboard. So we have done some experiments and we have seen some use case scenarios. One is the worst case and best case scenario for a setup for both simulations. So we have built a custom-made simulation because here it's a use case associated with video analytics. So the existing simulator couldn't meet our requirements. At the same time, we have done again some experimentation set up with a set of Raspberry Pis. We have done basically also a cost evaluation with how many VMs you need for particularly for a surveillance case. So we have seen the difference between a greedy algorithm versus a proposed algorithm, and then you will see what will be the cost, all right? So you'll see the required time for versus the case of the greedy algorithm in terms of the time to process an application. Also, we needed to consider a caching capability. The caching capability is about when a node executes a virtual function for data related with a data instance, for example, a video frame. It needs to be stored in a stack for a specific time. So in case another video analytics service requests that to process the data, it retrieves the results and forwards them to the next VM without recalculation. So that's why it needs the storage. And of course, the VF replicas can synchronize their cache's memory. Again, we have a similar problem from the migration aspect. The migration here, don't forget, is a migration of a specific video analytics. Again, we need to consider hardware and software capabilities. The whole idea here is the difference is that when you do the migration, since you have the service linked with a virtual function orchestrator, when you switch a virtual function to a new instance, this needs this implies that also the virtual function orchestrator needs to be updated as well. So we have done also the migration. This is I will call it the application type of migration at the edge. Um, so again, we have considered two migration scenarios, again, stateless and stateful. So by failure in the stateless migration, we consider a net that fails and disconnected from the virtual chain. So that means I need to restart the service again. Or in stateful, that means due to the capacity, the low capability of the edge devices, along with the increased demands of the edge service, it's not unusual for of the edge device to become overloaded. And then we have used two different approaches, the hard one and the soft approach. Call migration, it's called post-active. This is something that can be invoked by the orchestrator. All right, where live migration is the pre-active, when the QS monitoring generates some alerts to predict that the next node can be overloaded in the next time period. And of course, in this case, again, I don't want to go on details. We have used, again, the similar LSTM model to do this kind of prediction. So in terms of the evaluation of the deployment, we have used a kind of different frameworks. The first one, first of all, is the simple monolithic approach without any intelligence. That means I don't have any virtual functions. I have just assuming that may have a kind of device like NVIDIA where I can deploy the service. The second approach is to have the simple data distribution model that extends the monolithic approach, deploying the same service on several edge nodes and by distributing the incoming data to the nodes. And we've got another framework that we have considered, which is it's quite popular, the Apache, which is a general purpose distributed system that can utilize the processing capability in a kind of a cluster environment to perform complex computation like the ones that we are presenting. And we have done also some experimentation, as I said, with a set of Raspberry Pis, all right, with certain capabilities. And we have used a particular data set, in this case, VRAT data set, video data sets. So the whole idea here is we've got a set of experiments that have been conducted, and the whole idea is to report the performance of the proposed models. The aim of these experiments is to assess the scalability and the sustainability of these virtual function chain models. Also, the experiment set out to assess the contribution and the benefits of the services of the VFC. That's the first one is the caching that I have mentioned, as well as the migration. And of course, to compare the VFC, which is somehow a virtual function chain that has been targeted for video analytics services, and how to compare that when somebody will use an alternative frameworks like the Apache framework that I have just presented. So if we move to the next slides, we have done a kind of setups. So we have three different setups. So the first setup is related to the fact that the surveillance has been implemented under a monolithic approach. This means that its service has been hosted in one edge device. All right. The second scenario is the service has been implemented under a simplistic distributed method, where its surveillance service would deploy to multiple edge devices. And the third setup is our proposed model. So if you see, The first figure on the top, you'll see the total cost for different number of services in terms of CPU time. So you'll see our model gets better results, of course, if you have a small number of nodes when you have limited capabilities. Of course, you don't see any difference, but the difference is more evident when you have more devices because of the more distributed computing capabilities, so the algorithm can be able to make better decisions. The same also is when we do then make a benchmarking about the number of edge devices for different number of deployed services. All right, so you see on the vertical the number of devices versus the number of services. So again, you'll see in other performance. Also, another aspect is we have done also comparison between monolithic versus the proposed model for different types of video services in terms of whether this is high definition or right. Another aspect is to see the scenario that we can benefit when we are introducing caching. All right, so you can have the caching plus the QoS monitoring aspect. So you'll see the total cost of the case and the processed. So you will see if I have the monitoring, the QoS monitoring, I can have a benefit in terms of also the processed frame per second. And the same applies when I'm also introducing also the QoS mechanism. Of course, another aspect is when you take into consideration not only the number of devices, but also the video resolution itself. How many devices? Of course, it is expected as the increased resolution from 640 to HD, the number of devices goes up, and of course, this is also depends on what kind of backhauling capabilities I've got. So in this setup also, we have considered different technologies ranging from DSL to 4G and finally to 100 megabit. Yeah, I think I should present this. Yeah, another aspect, as I said, is, and this is also important, is to do the evaluation of the migration model. So we have considered in the first setup the QoS prediction model that not deployed. We have considered only call migration. When the second setup, we have considered the QoS. So both cold and live migrations have been considered. So what is important to see, an interesting part, is how to be able to consider the total time in different phases for this kind of application. So you'll see here, a first part, a small portion is when we need to identify as a percentage, very low percentage of as an event about the node, the next node, which is about to the checking point, all right, that something is going to happen. The second important aspect is the dump, all right, of the container dump. So this is a snapshot. Like the previous examples, you will see the sending the migration, which is almost a very large percentage, all right. Then, of course, the restoration, the container start when you restore the container, right? And finally, we have the virtual function update, all right? Don't forget, this is an application, so once you are sending the virtual function to a new instance, yeah. And of course, another experiments we have done also for this kind of setup is the downtime, and of course, we have considered different probabilities of occurrence. So we have measured the downtime and for different types of nodes, and as expected, of course, this downtime can go up if of course, this probability goes up as well. Again, similar examples of comparisons. We have, as I mentioned, done also some experiments with also a simulation environment and make a comparison against the Raspberry Pi deployments, and similar findings actually have been done. So make a comparison between cold migrations versus cold and live migrations, and as you will see, always the combination of cold and live can give much better results for different types of demands. All right. What I have done so far, what I have presented in this set of slides. In this set of slides, I have described, if you like, present something related to the deployment of a service in an edge environment. In this environment, we have made some assumptions. The assumptions is that how I can deploy multiple services on the edge, and services that are quite demanding, like the video analytics, and how that can be done by taking into considerations two factors. First one is how to be able to use even low-cost devices. For example, in this case, this can be the case of Raspberry Pi. How to maximize the capabilities, right, of the edge devices, fully utilized. And in order to do that, you have mainly to introduce the concept of virtual functions. That means I have to distribute, to decompose, if you like, a monolithic applications to several small processes. All right. This implies that I have a placement problem to identify where these virtual functions can be deployed. And once this is done, then you need a virtual function orchestrator that needs to bind all of them together. So this is also, besides the placement, I have also another optimization problem from the real constraint. That means when I bind all these virtual functions together, I need to make sure that I have a total time budget, which is how long it takes for the entire application to run and to present the results to the end users. And of course, in this kind of approach, what is important to consider is to consider the fact that certain virtual functions needs to be replicated. All right. Why is that? Because the same virtual function can be shared among different applications that can be deployed. Further advances, innovations in this kind of work is about, first of all, to do the QoS monitoring. of what is happening on the orchestrator and to act in a proactive manner regarding that. And in this also environment, a challenge, and if you like, a more challenge about the outages and failures that we have already seen in the previous set of slides as I'm presenting on the edge, is that when I need to migrate a virtual function from one edge instance to another, when happens, this is also implies that the virtual function orchestrator needs to be updated. So there is a much more complex process. I think before we move to the next part, which is the road ahead, I will make again a break here. So if you have any questions, I'm happy to answer. Give me a second. Yes. So I suggest, yes, do you have any questions?
Hello, sir.
Yes. Hello.
Okay, sir. Professor, such a nice session. Actually, our participants are very much interested with the topic, what you are delivering. Sir, one question from the participant is that what are the different optimization technique has been used in the VFC model?
Okay. Optimization is basically it's a hard NP problem because we have first of all two different constraints. One is the cloud constraint, so we can have the problem of finding the optimum node to allocate the different VMs. So this kind of problem, of course, depends on how many available instances you've got. And also you have a problem of the QoS aspect. In this case, it's the aspect of measuring the total latency. So the total latency depends how much you need to process each video frame to extract, for example, if I have feature extraction, or if I want to run the CNN. So each node needs to be processed, and then the other aspect is the outcome of this VF needs to be also sent to the next one. So it's a complex problem because we have these two constraints, but definitely the problem has to be somehow relaxed to be able to find a solution at the end of the day, which is also quite important from the allocation point of view.
Okay, sir. Sir, as the whole research work related to the cloud computing, so it is related to network. So, what type of security threat that you have faced or you want to solve during your research?
Yeah, okay. It's a good question. First of all, from the security point of view, it's not actually security, it's a privacy issue. Especially when you deal, at least this is a problem started a long time ago, when all these hyperscalers that are mainly US companies that they started to operate in Europe. In Europe, we have a framework regarding which is called GDPR, which is the privacy aspect. For example, when you deal with personal data, you must comply with the privacy issues. So in certain cases, the hyperscalers, they haven't considered any GDPR policy. They didn't have any GDPR policy, and for that reasons, there are a lot of penalties that have been introduced, mainly by the European Commission. Things have already started to improve. Of course, there is already GDPR policy adopted, but at the end of the day, there are certain, let's say, organizations, and I can give you an example in the case of, for example, let's say police. The police or similar organizations, they don't want necessarily to go and have, let's say, CCTV cameras and the video feeds deployed in AWS for various reasons. So in this kind of use case, this kind of infrastructure, which is a kind of a private cloud infrastructure, can be used to analyze the information.
Okay, sir. Thank you, sir. Thank you very much.
Yeah, yeah. Just to highlight, this is at the moment, and this is something that I also can present at the final stage of my presentation, which is about there is a lot of evolution goes on in the area of edge cloud. We have come across the last years a lot of companies investing and developing solutions. A typical example is NVIDIA with JSON. That means you can have an edge device with a edge AI processor. That means you implement AI models at the hardware level. And this is important in order to be able to highlight the aspect of the real-time constraint. Any more questions?
Sir, another last question is that, sir, how we have monitored QoS of the VFC, virtual function chaining.
Yeah. Okay, that's a good question. So first of all, we need to consider that we have the frame per second, which is the requirement from the input feed, all right? How many frames per second? Let's say 50. Let's say frame per second. It can be, let's say, your frame rate from your video feed. You can determine what could be your frame rate on the service, because the frame rate that I'm considering this work, we are considering this work is the frame per second of the service. So, for example, if I have, let's say, a service and I'm interested for a video, a face detection or a human detection or a face recognition, then of course this cannot be at the same level as the initial video feed. It can be much lower. This can be defined, let's say, by whoever deploys the service. So, for example, it can be, let's say, 20 frames per second. Your what you're going to display. So this, at the end of the day, can be used as a constraint on your virtual function orchestrator.
Yes.
If you are interested for this kind of work, of course I can. When I finish the presentation, I'm going to share with you the slides. So whoever is interested, you can have a look also on the papers as well. We can have more
Yes. Then we and
results.
as well the participants will be very much
Okay,
work
sure.
on the topic.
Okay, sure.
Sir, have we end the session or it will be
No,
continued?
how many more minutes do we have? Because basically, I just want to describe a bit of. I need I would say around 15 more minutes, if it's okay, to present the road ahead. Are we okay with? Are we okay with that?
Okay, 10 to 15 minutes is okay, sir. Okay,
All
make
right.
it.
Yeah. Thank you very much. Thank you. So mainly, what is important is to go to see at the end of the day what is the road ahead. Everything that I'm going to describe is under the pillar what is called 6G, because 6G has already been started across the globe. At the end of the day, somebody may ask, we haven't even seen 5G deployment. Why we need 6G? IMT 2030 have already identified some use cases. The first one is the integration of sensing and communication. The other one is immersive communication, the combination of AI communication. Again, we need to improve the reliability further. Also, can have ubiquitous connectivity and massive communication. So, because of that, we have new capabilities, starting from coverage to sensing, AI, sustainability, interoperability, and positioning. So, 6G have already defined a lot of areas. I'm not going to talk to all of those. It's starting from terahertz communication, joint communication and sensing, to AI and machine learning, reconfigurable intelligence surfaces, photonics, ultramassive MIMO, new network topology, and security. My talk is more again is going to be how AI will play an important role on 6G. First of all, the key question is why we need AI in general in telcos, all right? Not necessarily only on the edge of what we have seen so far. The reason for that is that networks and infrastructure optimization is important to optimize the services. And of course, at the end of the day, we need to consider the fact that the OPEX in any telco infrastructure must be further minimized. Also, we need to support the life cycle and operational process for managing the services, the application, and the network infrastructure. And finally, the services and applications offered to customers and the enterprises. In UK, we have a program which is called the UK Tele Network Program, and we have started producing some white papers. One of the white papers that was published last month, we describe, we have identified three different main pillars about using AI in telcos. The first vertical axis is about using AI on network and infrastructure domain. So how AI can be used in new technologies like O-RAN, or how you can enhance that in technologies like the edge, even from the standardization point of view, moving to the core network and towards the fixed and wireless access. Another area is the services and application domain, moving from the retail broadband to mobile 2B and 2C services, and from the enterprise to private cloud. And finally, in the productivity and effectiveness, moving from the strategic and operation to operation and assurance, fault management, security, and privacy. An important element towards this evolution to 6G is what is called knowledge-defined network. It's not a new necessarily concept. It's basically the KDN aims to improve what we've got as a self-organization. This is a concept that has been introduced in 4G networks. It's a cycle moving from self-configuration to self-learning, to self-optimization, and self-healing. Now, the whole idea here is how to use AI so the cycle can be autonomously operate, right, without any human intervention. That's the whole idea. So mainly, the standards are looking the technological options, and we've got two fundamental innovations on AI. One is the generative AI, the other one is the discriminative AI. The first one, if you like, for the generative AI, the whole idea is to basically to create a new kind of data, so to do data synthesis and augmentation in order to get new results. Or in the area of discriminative AI, the whole idea is to minimize the errors to improve the accuracy. So from the standardization point of view, all right, when we say standards, we're talking about the networks and whoever defines the networking standards on 6G. We have various deployments of AI and machine learning. The first approach is called independent AI machine learning, when the machine learning can be deployed independently either at the network side or at the device level. We are discussing about proprietary machine learning deployment and data collection, so there's no any synergy. Another option is the coordination between network and device. There can be proprietary as well as standardized ML procedures, where data collection are used for both training and monitoring and inference. Finally, we are discussing what is important. The transition is what we would like to move is what is called native AI, which is the autonomous ML deployment between the network and the device across all layers. So there are ML procedures that to train, but of course can adjust because the environment can be dynamic as well. So we are moving from DevOps, what is called MLOps. So an important element in 6G is called native AI. What is native AI? It's about the AI capabilities which is available or exposed for networks, but of course for services as well. The whole idea here is to split the entire AI system to multiple subsystems based on the specific objective of the service. And the component is then integrated to the service function of the service to provide an output. So the split AI approach can follow a kind of distributed kind of architecture. So can have a distribution in terms of data pre-processing to the training and to the inference as well. There is a very interesting report by Ericsson that was published a few months ago. So the whole idea when we discuss about native AI capabilities, first of all, Ericsson has defined 6 different levels, starting from level 0 when there is no AI at all engaged in your architecture, moving towards level 5, which is the full autonomous system. And then you will see we have different aspects of the native AI, moving from the architecture to the collaboration to data management, storage and processing to model LCM and security, up to any kind of self capabilities. Also, a very interesting, let's say, finding comes from Camp Gemini that a few months ago they released a very interesting survey. So they have asked 113 large CSPs about this evolution, right, about the network autonomy with respect to the levels as just presented in the previous slides. So according to this report, you will see most of the telcos, they think that by 2028 we have been moved from level 1 that we are currently level 1, a bit of level and level 2 towards level 3. So as you understand, we have a very long road to move forward to reach to a full autonomy, which is level 5. So in this cycle, as I mentioned also before, we are moving from what is called DevOps to MLOps. The MLOps, while DevOps optimize the life cycle of any big data project, the role of MLOps is mainly to solve problems associated with MLN production, in our case, about all telco life cycle. What will be the requirements? First of all, the requirements we need to take into considerations. We are experiencing an environment with there's an evolution of the computer architectures. We have seen so far technologies like hardware infrastructure, like GPUs or FPGAs or data processing units, but we have currently started to see new kind of hardware, the neural processing units. This is about implemented complex neural network models at the hardware level. Another important aspect is in this heterogeneous environment, there is an aspect and we expect to see how AI can manage in a more efficient manner the outages. But now the challenge is that I don't have a single homogeneous hardware environment, and the environment is heterogeneous, and this is something that implies that we need to improve the orchestrations to handle that. And of course, another aspect is how to facilitate the automation of the network using a kind of intent-based approach with using LLM. So in practice, you may have somebody that can manage a very complex network infrastructure, and the whole management can be done through an intermediate, which is going to be an LLM system that will be able to interact with even a non-expert and translate these requirements to something that can automate the process within the network. In this kind of course environment, when we do the transition, we have a lot of challenges. Challenges is first of all how to manage the data errors. Data errors can be because there can be no accurate measurements because of a noise. It can be missing values or records from the fact that we have different telemetry systems that can be collected by different devices. We may have problems associated with data anomalies because of things like data poisoning. We can have somebody who can be an intruder that poison the data. As you understand, in this kind of environment, this is something quite challenging. There's no currently solution to that. And of course, what happens is when these records needs to be communicated and they suffer a delay, what will be this impact on the inference? So, coming from this point, there is a growing demand for what is called AI area networking. This is how to transform the existing data networks to handle this data. Now, what's the difference? Existing data centers, the main aspect is to handle this data transfer without any bottleneck. In this case, the whole idea here is how to manage not only the bottleneck, not only the data transfer, but also the processing aspect because of the AI and other already approaches, how to extend, how to improve the network, the data center technologies, moving to technologies like InfiniBand or Ultra Ethernet that trying to take into consideration all the challenges that I already mentioned. And finally, I just want to mention to you that a couple of different organizations, all right, in telcos, then they see that they have been looking at AI, all right, the role of the AI. So first of all, it's the International Telecommunication Union, which sets the goals for 6G, what is called IMT 230. We've got the European Telecommunication Standard Institute, which is basically have different working groups, securing AI, the network intelligence, trust, network function virtualization, open CAPIF, and open slice. We've got the 3GPP, which is related to the mobile world. From the architecture point of view, in 3GPP, how we can do the operation splitting on the AI, how we can do the data distribution and the sharing, how federated learning and distributed learning. And I didn't have much time to talk about federated learning. The advantage of federated learning is you can share not the data among different providers, but also only the model data. And this can be used to improve the accuracy of these models. And of course, the whole idea of changing the way that we are implementing things, even how you can use AI to do some classical radio functions like beamforming, load balancing, energy saving, radio resource management, so all these traditional radio functionalities and optimization, how this can be done with the AI. Yes, I try to be quick, as I promised, try to keep my presentation, the last part, in 10-15 minutes. In any case, I'm going to send you the slides so to share it with anybody. Yeah, if you have any questions, don't hesitate, of course, to drop me an email. But in the meantime, if you have any questions regarding the last part, I'm happy to answer the questions.
Yes, sir. Thank you, sir, for your valuable time that you have given for delivering this fantastic session. And actually, so many questions I have asked, and you have given all the answers regarding this. So once again, thanks to you. and
All right.
thanks the whole team,
All right.
especially.
Okay. Thank you. All right.
And in
Thank you very much.
future, we want to touch with you. Thank you, sir.
Okay.
Thank you so
Sure.
much.
Sure. Thank you. Thank you. Bye bye.